So let's start with part 1, warm-up question. Question A says, briefly describe the concepts and utility of 1. Programmable pipeline stages, 2. Shaders, and 3. Rasterization. Give examples where appropriate. Before we start, let's briefly talk about the rendering pipeline. Each time your code calls a draw function, your model data, that is your vertices, textures, etc., is processed in the pipeline to produce your final result or your final raster image. But first, to be able to perform any rendering, we need to do two things. We need to create vertex buffer object and a vertex array object, and this corresponds with the vertex specification step on the diagram here. And we need to create shader program. Just as a reminder, vertex buffer object contains your vertex data, while vertex array object provides information about the format of the data and the organization of your vertex buffers. In other words, it tells OpenGL how to interpret the data from your vertex buffers. Let's get back to the question. Rendering pipeline is a set of stages or steps that are taken to render objects. Stages such as vertex processing, tessellation, geometry processing, and fragment processing are programmable, which means that we can write our own custom GPU programs, which will then be used to process data in the pipeline. These programs are called shaders. Shaders that process vertices are called vertex shaders. Shaders that process fragments are called fragment shaders. And the same is true for tessellation and geometry shaders. Rasterization. Rasterization is a process of converting geometry data into an array of fragments. It's worth noting that in APIs such as OpenGL, vertex attributes are linearly interpolated across fragments. Question B. What is the role of element array buffer? Element array buffer is just another name for your index buffer. We've covered it last time, but just as a reminder, we use index buffer to enable vertex reuse and avoid vertex redefinition. The main advantage is that we can optimize our models so they require less memory to be stored and less computations when we calculate transformations, as there's a smaller number of vertices that we have to deal with. Question C. Explain the difference between in, out, and uniform variables in GLSL. In variables define input of a given shader or a given stage. In case of vertex shader, they directly correspond with vertex attributes. Vertex attributes can include anything, but usually include positions, normals, UVs, colors, etc. Let's look at the example. Let our vertex be defined by 4 attributes: position, normal, tangent, and texture coordinates. In C++, we can define vertex as a structure that looks something like this. So we can think of our model as a list of vertices. On the application side, as usual, we first create vertex buffer and upload our vertices to it. Then we create empty vertex array object and link it with our vertex buffer. To remind you, the role of vertex array object is to tell OpenGL how to interpret our vertex data. These 4 lines define the data layout of vertex attributes. In other words, they inform OpenGL about the vertex data structure layout. These next 4 lines enable these attributes, or in other words, make them visible to the vertex shader. So now that we've enabled our vertex attributes, we can quote-unquote see them or receive them in vertex shader. So that's in variables. Now let's talk about out variables, which are another important mechanism for communication between shader stages. Out variables define outputs from a given stage. For example, if we wish to pass a transformed normal from our vertex shader to our fragment shader, let's say for some per fragment lighting calculations, in our vertex shader we create an out variable of the type vector3, called, for example, normal. And we assign transformed normal value to it, also in vertex shader. To receive it in our fragment shader, we create corresponding in variable of the same type there. Note, however, that the normal we will receive in our fragment shader will be an interpolated version, interpolated across fragments. We've covered in and out variables. Now we know how to communicate between shader stages. It would also be quite handy to be able to communicate between CPU side of your application and the rendering pipeline. This is where uniform variables come in. Uniform variables are fundamentally different from in and out variables, as they are not used to pass data between stages. In fact, as opposed to, for example, per vertex or per fragment changing values, such as positions, normals, or colors, uniform variables remain constant during draw call, or uniform across all shaders. That means that our application code running on the CPU side can update uniform variables in between draw calls. A great example of using uniform variables is passing our model view projection matrix to our vertex shader. We can see that this is very useful, as we usually want to transform all of our vertices in the same way using the same matrix. Another example would be passing texture references to fragment shader. This also makes sense, as we want all fragments to be sampled from the same texture. Usually we want all fragments to be sampled from the same texture, or at least we don't want each fragment to be sampled from a different texture. That wouldn't make much sense. This wraps up the first part of the assignment, warm-up questions. Part 2. Pipeline and rendering. Question A. How could you achieve the effect of reflective surface, for example water, in your OpenGL or D3D application, utilizing functionality provided by the API, instead of ray tracing? Ray tracing is just a matter of tracing another reflected ray and later combining colors sampled from different hits. While this gives us great results in terms of quality, it is not really feasible to do in real time, or at least with decent FPS. And this is true especially for large amount of complex objects, so nearly all of the typical customer applications. So we need a workaround, something that would utilize built-in rasterization and yet produce still good enough results. This is where a technique called multipass rendering can help us. So as the name suggests, the idea is to render a frame in multiple passes. But what is a render pass? Simple answer is, render pass is a process of rendering elements of your scene, or your entire scene, to a buffer. So under normal circumstances, or in single pass rendering, your buffer is the screen buffer, or your target buffer is your screen buffer. But here, each time we draw something, we don't render to this default frame buffer. This means we don't display the results on the screen right away. Instead, we render to our own customly created buffer, to which we can attach, for example, an RGB texture. This means that the scene we render will be rendered to that texture. Then later, when we produce our final frame, we can use that texture in the same way we use textures loaded from image files. So knowing this, we can now think of a simple example of rendering reflections, such as water. Now for the flat surface, we will probably get away with using just one additional render pass. So now let's go through the process of rendering scene with water reflections. First we do setup, which means we create our vertex buffer, load our textures and compile shaders as usual. Then we create an additional frame buffer and a render texture. And then we attach this newly created render texture to our newly created frame buffer. And setup-wise, this is pretty much the only difference. Now we bind our new frame buffer as a target buffer and we render our scene from the point of view of the water, or as water sees it. We call our draw call. The scene gets rendered to the texture. Now that we've done it, we are ready to do our final pass, where we will use the texture that we've created to texture our water mesh. Now we can bind the default screen buffer as a target, so we will render to the screen now. Of course, we can mix the colors sampled from that texture however we like. One example is shown here on the diagram. We mix colors sampled from our diffuse map and our reflection texture, which we've created in a previous pass. We use linear interpolation and we parameterize it with a value from the reflection map. This is of course just one example of mixing colors. We could just use the reflection texture alone if we wanted to, but usually it's good to mix it with some older diffuse map, or maybe if we want to have a more complicated surfaces that are reflective in certain regions but non-reflective in others, having a reflection map is quite useful. Just as a side note, for shapes that are more complicated than flat surfaces, we usually require building some sort of environment map. In OpenGL we can use cube map. This means that instead of rendering the scene from the object's point of view just once, we render it 6 times, and each time for the same position, but changing camera orientation. So we render one for left, right, front, back, up, and if we need, down. Then later, instead of sampling 2D texture with UV coordinates, we sample our cube map with normals. Question B. Texture tiling is used to map UV coordinates outside of the 0 to 1 range, resulting in a repeated pattern. Search for other texture wrapping techniques and describe them here. So let's have a look at some examples of texture wrapping techniques. First, in the upper left corner, we can see a standard repeat tiling. This is the type of wrapping that I've described in my question. So if we set texture wrapping mode to GL repeat in OpenGL, this is the result that we will get. It's an equivalent of modulo 1 operation on our texture coordinates. And below we can see this UV mapping illustrated as a graph. Another type of wrapping is called mirrored or mirrored repeat. If we set texture mode to GL mirror repeat in OpenGL, this is the result that we will get. I like to think of this mapping as a triangle function. As we can see from 0 to 1, we get our UVs as usual, and then from 1 to 2, we get the mirrored version. Then from 2 to 3, we get mirrored version of a mirrored version, which is a normal version. And then again. Mind you, this happens for both x and y dimensions, of course. The next type is called clamp to edge. This means that values from 0 to 1 will be sampled as usual. Then for UV values smaller than 0, we will get the color of the first pixel. Analogously, for values greater than 1, we'll get the color of the last pixel. And finally, clamp to border wrapping mode. Here the sampler will give us default border color for values outside of the range 0 to 1. Otherwise, we will get our texture color as usual. Question C. Explain how each of the following techniques can add detail to a flat surface. Discuss the benefits and potential limitations of texture mapping, normal mapping, and displacement mapping. So let's start with texture mapping. It allows us to add flat texturing to our three-dimensional objects. We can control how the object is textured with texture coordinates and texture wrapping modes. While it helps us to enhance the appearance of a surface, apart from changing surface's color, it does not influence the way in which light interacts with it. At least not to the same degree that normal mapping does. So the main idea of normal mapping is to introduce fake details to the surface. We use normal mapping when we want to improve the appearance of low polygon models. The main idea is to perturb our normals in fragment shader using values sampled from the so-called normal map. Because we use normals for lighting calculations, these perturbations will have an effect on our final result. So what's a normal map? Well, fundamentally, it's just an RGB texture, but instead of using it to store colors, we use it to store normals. This basically means that our RGB channels are just used to store directions of our normals, X, Y, and Z. So where do we get our normal maps from? We usually generate them from high poly versions of our models. I think it's important to clarify though that it's not our application that generates normal maps. These are usually provided to our applications along with models. So what are the main advantages and disadvantages of using normal mapping? We get improved appearance at relatively low cost, at least when compared to using high polygon versions of our models. But geometry is basically not affected by normal mapping. And this means that illusions will break at extreme viewing angles. And that's because silhouettes of the objects are not affected. And since we usually calculate our shadows based on our geometry, shadows will also not be affected. Displacement mapping is different in this respect. Here, instead of using normal map to fake the light interactions with geometry in fragment shader, we actually modify geometry based on the input from the height map. The upside is that we get correct shadows, we get correct occlusions, and we can see the effect on the silhouettes of our objects. The downside is that we need to create a substantial amount of new vertices on the fly, so there's a performance hit. Question D. Multiple resolution versions of a texture can be stored as Mipmaps. Explain what are Mipmaps and how are they stored in memory. What are the advantages and trade-offs of using them? Mipmaps are essentially pyramids made of lower resolution representations of the same image. They are generated when the texture data is updated, given that the Mipmap option is enabled. Each consecutive level with the index I is a quarter of the size of its predecessor, I-1. Or we can think of it as 1/2 raised to 2 times I of the original image size, where I equals 0 is the index of the original base image. So what are the reasons for using Mipmaps? Well, mainly they provide us with a texture level of detail. For example, when our camera is far away from our textured object and we need a smaller version of a texture, rather than downsampling it each time, we use already downsampled layers from Mipmaps. The upside is reduced computation cost in comparison to other real-time filtering methods. This, however, is only true if our texture content doesn't change too often. If our texture changes, OpenGL has to recalculate our Mipmaps. Now, it rarely happens that the particular required texture resolution matches exactly the resolution of one of our Mipmap levels. Usually the closest level is used. However, if we activate trilinear filtering, OpenGL will interpolate between two closest levels to get the final sample value, giving us smoother results. So what are the disadvantages of using Mipmaps? Well, the main one is increase in required memory by exactly 1/3 of the original texture size. Why 1/3? By looking at the diagram, we can already intuitively see the answer. But we can also deduce it from the fact that the sum of areas, which is the summation of 1/2 raised to 2i, converges to 1/3. Question E. What is alpha blending? And question F. Explain the meaning of the following line of OpenGL code. GL blend func, open parenthesis, GL src alpha, comma, GL1 minus src alpha, close parenthesis. Alpha blending allows us to render translucent objects. And it's a process of mixing a translucent foreground color with what's in the background, and as a result producing new color. GL blend func allows us to specify how OpenGL should blend foreground with background, or with objects in the background with the color of the current object. First parameter corresponds with the amount of foreground color. In this case we have GL src alpha, which means that OpenGL will multiply the foreground RGB with the foreground alpha value to get our final foreground contribution. Second parameter corresponds with the amount of background contribution, or background color. In this case we have GL1 minus src alpha, which means that to get contribution from our background, OpenGL will multiply our background RGB triplet with the value of 1 minus foreground alpha. As a result, we get a linear interpolation between foreground and background colors. And this linear interpolation is parameterized with our foreground alpha channel. So this wraps up part 2, pipeline and rendering. Part 3. Vision and color. Question A. What are metamers? Describe a practical application of metamerism. Metamers are colors that appear to be the same to us, or you can say trigger the same perceptual response, despite having different spectral composition. Wavelengths that human eye is able to perceive range from around 380 nanometers to about 720 nanometers. A retina contains 3 types of color-sensitive cones that differ in their response to short, medium and long wavelengths. This diagram shows response characteristics of each type. Short-sensitive cones response peaks around 440 nanometers. Medium peaks around 540. And long peaks around 580 nanometers. Now, to produce a color, we can take it directly from the spectrum, in which case we would call it a spectral color, or we can create it by mixing light of other wavelengths. So if we take a look at this diagram here, on the left side we have a yellowish-orange spectral color produced using light of around 600 nanometers. This 600 nanometers wavelength stimulates all three types of cones on our retina, but to various degrees. So let's take another look at the diagram showing response curves of our cones. These response curves are normalized. We can see how much our 600 nanometer wavelength stimulates each type. Short wavelength sensitive cones are barely stimulated, giving us response of 1/1000th on a normalized scale, which is 1/10%. Medium wavelength sensitive cones are giving us 38%, and long wavelength sensitive cones responding with 84%. When our brain looks at these numbers, it generates the perception of yellow-orange. The interesting part is that we can also achieve the same level of stimulation of each type of cone using separate wavelengths. Let's say we decide to mix the following wavelengths as our primaries: 700 nanometers as red, 546 as green, and 435 as blue. Now, we adjust the intensity of each primary color to make sure that they stimulate corresponding cones to the same degree to which our 600 nanometers wavelength did. And we should get the same yellowish-orange color. And there we have it. The color on the left and the color on the right are metamers. They are made of different wavelengths, but they cause the same perceptual response. The question also asked about applications. Can you think of one application where we mix primary colors to get the desired outcome? Chances are that you own at least one device that takes advantages of metamerism. So the answer is pretty much most of color displays that we use today, at least the ones that use RGB primaries to produce color. In fact, if we take a look at the pixel from the close-up perspective, we can see that it's made of tiny red, green and blue stripes placed close together. From far, thanks to our inability to perceive very high spatial frequencies, these red, green and blue primaries blend together to give us the final color. This leads us nicely to question B. Describe the use of each of the following color spaces: RGB, sRGB, HSV, XYZ. How can you convert between them? So let's have a look at the RGB color space first. It's a three-dimensional space where each dimension represents one of the primaries. It's usually visualized as a cube. The resultant color is a combination or sum of our three primaries. Mathematically, we can think of RGB triplets as of 3D vectors. In fact, in many programming languages, they are often represented as vectors. Apart from displays working in one or another variant of RGB, there is a multitude of other examples. Most image editing software allows for color manipulation in RGB. Now sRGB. sRGB stands for Standard RGB, and as the name suggests, it's a type of RGB color space. Its goal is to provide device-agnostic representation of colors. In other words, it helps us to ensure that the same RGB signal values are interpreted in the same way across applications and devices. I like to think about sRGB as of the world's default way of communicating color. It is now adopted internationally by a multitude of industries and many devices. This includes our cameras, displays, printers, and many more. Now possibly, at least once, you have walked past the TV aisle in a shop and saw the scenario similar to this. We have many displays showing the same image, yet the colors displayed on each one of them appear to be rather different. Why is that? Well, it's obviously because they map the same RGB signals to physical colors differently. There could be many reasons for this. Main reason is different physical device characteristics. For example, technology used to build these displays could be a factor. For instance, OLED displays have much wider gamut than LCD displays, and because of this, they will differ in terms of response characteristics. But we can also have two displays of the same type, for example, two LCD displays, and yet individual differences between manufacturers and even device models will have an effect on the final displayed result. Less relevant, but I should also mention different user settings and profile, as of course they will have an effect too. So the goal of sRGB is to provide standardization or a common denominator for all these different devices. When working in sRGB mode, all displays, regardless of type or manufacturer, should display any given RGB triplet in the same way or as the same physical color. For some displays, this can even mean narrowing down their color gamut just to comply with the standard. So what's the point of this? Well, it allows us to tie any particular RGB triplet with a physical color. And as you can imagine, it makes everyone's life a lot easier. Web designers, user interface designers, graphics programmers, and all kinds of artists can communicate using the same standard. And as you might expect, sRGB standard defines exact chromacity values of red, green and blue channels. It also defines nonlinear relationship between channels intensity and channels value. This is often approximated with a gamma value of 2.2. Now, the transformation between real physical values and sRGB is a form of forward display model. The role of forward display model is to translate physical quantities, physical wavelength values, into digital values that we can use to drive our displays. We will be talking a little bit more about it when we discuss XYZ color space. But now let's talk about HSV. HSV stands for hue saturation value, and it's a different way of representing colors. Many people consider it much more intuitive way of thinking of colors than in terms of primaries. It's widely used by artists and graphics designers, and as a result, image editing software usually includes tools for adjusting colors with reference to HSV or HSL space. Separating hues from saturation and intensity is often useful in computer vision too. For example, in color-based feature detection, being able to separate colors from the lighting conditions is quite handy. HSV space can be visualized as a cone. Hues are arranged in a circle around the central axis. This central axis ranges from black at the bottom to white at the top. Now let's talk about CIE XYZ. I like to think of this color space as a sort of ultimate color space. It provides standard reference for all other color spaces. It's a space that ties them together. All color spaces can be expressed and compared in XYZ. Using familiar analogy, we can say that XYZ is like our world space, where other color spaces are kind of like object spaces. The only difference is that they are bounded. Particular positions are colors in this analogy. This also means that all color spaces that we've discussed before are a subset of XYZ. XYZ contains all visible color sensations, but it's not restricted to visible colors only, meaning that it can also contain impossible or imaginary colors, colors that don't exist in real life. And this is because pure XYZ primaries are imaginary primaries, which means that they actually lie outside of the visible gamut. You may wonder now, what is the point of having primaries outside of the visible gamut? Why is that? The short answer is that it is impossible to recreate all visible colors using a fixed set of real primaries. Let's illustrate this by looking at our visible colors gamut. These are all visible colors that we can see. We pick three primaries, right on the edges of the visible color. We get this triangle. So all of the colors that we can make are inside of this triangle, because they can be created as a combination of all these three primaries. So this is why we cannot recreate all visible colors with fixed set of primaries. In order to encompass the whole gamut, the space has to be larger. Given that XYZ primaries do not exist in real life, one may ask, where did they come from then? This takes us back to late 1920s, where William David Wright and John Guild separately conducted series of experiments which served as a basis for creation of XYZ color space, which happened in 1931. Wright's experiments included 10 observers. The goal of his experiment was to determine proportions of fixed primaries needed to reproduce the same color sensations as pure spectral colors do. Or, in other words, to find metameric matches for pure spectral colors. In each trial, observers were shown pure spectral color, shown here on the left, and they were asked to adjust intensity levels of each primary, shown here on the right, until both colors matched. Now mind you, this diagram is only for illustrative purposes. The physical arrangement of the actual experiment was a bit different. And of course, much more than 5 wavelengths were tested. Anyway, it was possible to find matches for many spectral colors, but for many others it couldn't be done. So Wright decided to move one of the primaries to the left side and then try to match the left and the right side. Now it was possible to find matches for all spectral colors, but it meant that some primary values became negative. If we look at the resultant color matching functions, showing us how much of a given primary we need to reproduce corresponding spectral color, for example here between 450 and 550 nanometers, we can see this negative dip for red primary. We can also see it when we plot the resultant gamut. This gamut, which is the result of our experiment, was used to create the granddad of all color spaces, CIE-RGB, which is very close to XYZ. Because CIE-RGB is a result directly derived from experimental data, it has a lot of flaws, especially these negative values. But it provides us with a unified way of describing color in an objective, numerical way. The next step was to make it more ergonomic and easier to deal with. Get rid of these negative values, clean it up mathematically. And this is what CIE 1931 XYZ space is. Cleaned up, linearly transformed CIE-RGB. We can now move from CIE-RGB to much more convenient XYZ with just a 3x3 matrix multiplication. Because linear transform is used to move from CIE-RGB to XYZ, we can be sure that all linear color combinations done in XYZ will be preserved in CIE-RGB and vice versa. And this is of course because linear transformation preserves linear combinations. And now that we've arrived at the answer how were XYZ primaries found, we can also answer why they are imaginary. This is because when we've transformed CIE-RGB real primaries to make things more convenient mathematically, they no longer represent primaries in the visible color space, but rather some abstract values, and that's why letters X, Y, and Z were chosen instead of RGB, to emphasize this. Okay, I think that's enough information about XYZ color space. Let's move on to question C. What is the difference between additive and subtractive color spaces? Give one example of each. So far, all color spaces that we've discussed were additive, meaning that they rely in one way or another on additive properties of light. We usually start with black or no color, and we keep adding light to it. In other words, when we think of color 110 or RGB yellow, we really mean black plus yellow or 000 plus 110. This is why additive color spaces are useful when we think of emission or radiation. If we take a look at the pixel from up close, we can see that it's made up of small RGB emitters, and as we've discussed, we can reproduce a subset of colors from the visible spectrum by adding RGB primaries. Subtractive color spaces are rather different. As I mentioned before, with additive color spaces we start with black or no light, and we add light together. In subtractive color space, we start with white and think in terms of what we need to subtract from it to get the desired color. In other words, we focus on which part of the spectrum gets absorbed by a given color to figure out which portion will be either reflected in case of opaque objects or let through in case of tinted transparent objects. So let's imagine a white light or 111 in RGB directed towards a white screen. We can see that the screen reflects all three primaries equally, or the entire spectrum equally. White screen also absorbs small but equal amount of each wavelength from the spectrum. Now let's place a piece of yellow tinted glass in front of our white light. The light of shorter wavelengths corresponding with perceived blue gets blocked. Only red and green components are let through. And as we know, combination of red and green gives us yellow. We can say that this yellow tinted glass acts like a filter for shorter wavelengths, but allows medium and long wavelengths to pass through. If we swap our yellow colored glass for cyan colored glass, we filter out longer wavelengths or the red part of the spectrum, while green and blue parts can pass through. And this also makes sense as full green and full blue in RGB will give us cyan. The same is true for magenta. Magenta tinted glass will filter out our green component of the light while allowing red and blue through. So there we have it, yellow, cyan and magenta. If we reorder it, we get cyan, magenta, yellow, or CMY. You have probably heard of CMYK color space. It's most known for being used by printers. You might have noticed that if you buy a color cartridge for your printer, the ink colors inside will be cyan, magenta and yellow. Let's talk about this particular choice of colors. In additive color spaces such as RGB, we start with black, and with each channel we control amount of just one primary. In subtractive color space, we start with white, but we also want to control, or in this case subtract, just one primary with one channel. And this is what cyan, magenta and yellow allow us to do. Cyan blocks red, magenta blocks green, and yellow blocks blue. So there we have it. Each channel modulates the amount of absorption of only one primary. This gives us the necessary control. Control that we wouldn't have if we used red, green and blue filters instead. For example, red filter would allow only red portion of the light through, so we would be blocking two primaries now, blue and green, not just one. I hope this answers why cyan, magenta and yellow were chosen. Now I would also like to discuss the K part. K represents black. We don't use letter B to avoid confusing it with blue. Now why do we need black? There are two reasons for this. So far I have chosen to illustrate the example using primaries and perfect filters that filter out all of the wavelengths. In real life our cyan, magenta and yellow colored ink does not act like a perfect filter. I'm not even sure if producing ink capable of absorbing all of the required frequencies from the continuous spectrum with such precision would be possible. If so, it would certainly not be practical. In practice, this means that even if we mixed all three colors together, we would not be able to get a good quality black, but more like a brownish black. Second reason for using black in CMYK is cost effectiveness. Even if we could produce satisfactory black, doing so with 3 separate pigments would be a lot more expensive than just using one black pigment. Question D. Gamma calibration of a display requires finding the exponent of the display's response function. We call it gamma. Typically, to find the gamma, users are asked to match 2 intensities or colors, reference and match, which are displayed against each other. Why and how is it possible for a display to produce the reference color or intensity correctly before it's calibrated? If it can do so before the calibration, why calibrate? So this should really be a star question, as it requires you to look slightly outside of the lecture materials. My goal here was to give you something that you couldn't just look up on your lecture slides. So before we can answer the main part of the question, let's think about how can we find a midpoint between minimum and maximum brightness produced by our display. We cannot simply trust our display that if we feed it a signal of I equals 0.5, we will get the right brightness representing physical midpoint between its blackest black and its whitest white. It is, after all, uncalibrated. What we could do is to use external device to measure the black level at I equals 0, midpoint level at I equals 0.5, and a peak level brightness at I equals 1. Then we could take the average of black and peak luminance to get our true reference, true midpoint. We could then compare this true midpoint with the luminance level that we've measured at I equals 0.5, and using logarithms calculate the gamma of the display. And this is basically what our next question is about. Most users at home do not have the expensive colorimetric equipment to help them calibrate their displays. But there is a way around it. It capitalizes on the fact that human visual system cannot perceive high spatial frequencies very well, and as a result, patterns containing such frequencies will blend. It is a phenomenon called optical blending. I have prepared a short demo for you. Can you see the image of a gray rectangle? It appears more or less uniform, right? Now, let's examine this image by magnifying it. On the right side, we have just gray color. But on the left, we have a checkerboard. 1 pixel by 1 pixel checkerboard, to be precise. And when this pattern is small enough, it will blend into gray. So this will happen when 1 pixel of the image corresponds with 1 pixel on the screen. The reason I have filmed my display with a camera instead of using screen capture is because I wanted to show you this optical blending really happening. You might already start to see where we're going with this. To produce this fake gray color, our display is only using black and white colors, or only 2 luminance levels, black luminance level and peak luminance level. They are represented by digital values of 0 and 1. We know that both 0 and 1 raised to any non-zero power will remain unaffected. So this means that the black at I equals 0 and white at I equals 1 will both remain unaffected by our display's gamma. And we can easily demonstrate it by doing a simple test in Image Editor. As we change our gamma here, we can see that only values in between 0 and 1 are affected. In our example, we are using all primaries at once, but the same idea is of course true for all channel primaries separately, as well as for all of their combinations. So now we know how to produce our objective midpoint between 2 intensities. All we have to do now is to display our pattern-based objective midpoint alongside gray produced by our display at I equals 0.5, and then let the user adjust the gamma until both sides match. The closest match will be the best approximation of our display's gamma. Now, the last question in this section asked you to calculate the approximated gamma of a display. So let's see, our reading of black level was 2 candelas per meter square. Our peak luminance was 350 candelas per meter square. And our luminance at I equals 0.5 was 65.934 candelas per meter square. So let's first normalize our luminance values so they fit nicely between 0 and 1. Let's start with subtracting L black from all of our values to shift our scale to the left. Now we can divide them by the maximum value to bring it to the 0 to 1 scale. So naturally L black normalized is still 0, L peak normalized is now 1, and L at I equals 0.5 is now 0.1837. So now we know that our driving signal of intensity 0.5 raised to displace gamma will give us the result of 0.1837. So to solve for gamma, we take the logarithm base 0.5 of our normalized luminance, 0.1837. And we get our answer, which is 2.44576468. or 2.4 to 1 decimal place.